Okay, here's the idea behind the word problems in section 1.5. We're going to be doing what are known as mixture problems, which means you're going to have a body of water. You might start with pure water, or you might start with water that has something dissolved in it, salt, pollution, whatever. You're going to have more liquid coming in, and the liquid coming in might have salt or pollution or whatever dissolved, and you're also going to have liquid going out. So what happens if you have something that's dissolved, that has salt dissolved in it, and you're bringing in more salt concentration, but yet at the same time you're draining stuff out? What's going to happen to the concentration of the salt?
Depends on the amount of flow.
It depends on the flow. It depends on the concentration coming in, depends on the flow rate coming in, and then it depends on the flow rate going out. So in general, if you have more salt coming in than what you already have in the container, the amount of salt is going to go up. On the other hand, if you have less salt coming in than what was already in the container, then the amount of salt is going to decrease. All right, so here's all the symbols we're going to have here. We're going to have x of t be the amount of solute at time t. So x of t is the amount of salt in the water, or the amount of pollution in the water, or whatever we're dealing with. X at 0, that's the amount of the pollution or the salt or whatever at time 0. Ci, this is your grams per liter of the solute flowing in. So C is used for concentration. This is the concentration of the amount of pollution or salt or whatever we're talking about coming in. Ri is the flow rate in. So this is how much liquid is coming in at any given time. And R0, or actually that's an RO, that's R for out. That's the flow rate out. So we've got flow rate in, flow rate out. All right, so think about any little given time interval. If X is the amount of salt or pollution or whatever, then what's delta X going to be on any given time interval? It's going to be the change in X, and the change in X stands for the amount of solute. So delta X will be the solute that comes in, but remember we've got liquid flowing in and we have liquid flowing out. So minus the solute that goes out. That will be our change in our solute. It's how much we added minus how much we took out. All right, so we're going to have the amount of solute flowing in for any given time is R sub I times C sub I times delta T. And let's just see why that makes sense. What was R sub I again? That was the rate of the liquid coming in, and that's in liters per second. And our concentration in, that was in grams per liter, and our time is in seconds. So we've got liters on top, liters on bottom, seconds on top, seconds on bottom. We're left with grams, which is the unit we would want. Why would we want grams in that case? It's an amount. It's the amount of the pollution or the salt or whatever that came in. That would be in grams. All right. The amount of solute flowing out depends on the concentration out. Now notice I didn't list the concentration out back up here. The concentration in the solution at time t is the concentration is X divided by V. So what are we talking about here? What's X again? X is the amount of the solute that's dissolved, and V is the total volume. So the concentration of the stuff going out, well, that's how you compute concentration. It's the amount you have divided by the total amount. So this is the amount of salt, the amount of pollution, or whatever we're talking about, divided by the total volume of our body of water. So notice that concentration out changes, doesn't it? Because the amount of solute changes. So concentration out is not a constant, it's a variable. And this can be even more difficult. Volume. Volume is not necessarily a constant either. Because we have water coming in, we have water going out. When is the volume going to be a constant? When those are equal. If we have more water coming in than we have water going out, then our volume is going to change too, isn't it? Our volume would be increasing. So volume can also be a variable. All right, so concentration out, that's usually the most difficult thing for us to figure out because that's X divided by our volume, and our volume can be changing. Okay, so our delta X, as we said before, this is the amount of solute coming in minus the amount of solute coming out. So coming in, we have the rate in times the concentration in times however long that's been happening. And going out, we have our rate out times our concentration out, remembering that concentration out is not a constant, it's a variable. Dividing by dt, we get delta x over delta time is rate in, concentration in, minus rate out, concentration out. And if we let delta t go to 0, we finally get down here a differential equation, or more importantly, we usually write it that way. And we notice that this is a linear differential equation. Because we have here x prime plus, then we have some variable here. We have r0 over v of t, x equals, and this one's just a constant, but this is x prime, and this is q of t x. I'm sorry, that one we call p. That one's our p of t, and this one's q of t over here. So this is in the form x prime plus p of t x equals q of t. We end up with a linear differential equation that we can solve. Questions on that? All right. That all looks very complicated. Let's see what it looks like in application. Assume that Lake Erie has a volume of 480 cubic kilometers and that its rate of inflow from Lake Huron and outflow to Lake Ontario are both 350 cubic kilometers per year. Suppose that at the time t equals 0 years, the pollutant concentration of Lake Erie, caused by past industrial pollution that has now been ordered to cease, is 5 times that of Lake Huron. If the outflow henceforth is perfectly mixed lake water, how long will it take to reduce the population concentration of Lake Huron to be, or of Lake Erie to be twice that of Lake Huron? Okay, so what's my volume? 480 cubic kilometers. In this case, it tells us our rate in and our rate out are exactly the same. Our rate in and our rate out are 350 cubic kilometers. What's our concentration coming in? Our concentration coming in is the pollutant concentration coming from Lake Huron. Right, so they don't give us a number for that, do they? So we just have to use a letter. So what letter do we like for the concentration coming in? CI, we're just going to leave it at CI? I'm just going to call it C. I think I like C. Is that?
Oh, I think that's over here.
Yeah, I'm just going to call this concentration. I don't know what it is. They didn't give us a number for it. So I'm just going to call it C for...
But don't we have to have it like CI equals 5C? We have to, that way when we get down to it's 2 equals 2C.
Okay, but you need to be careful. The 5C is something important. The concentration coming in is simply the concentration flowing in from Lake Huron. So you're answering the next question, what's X sub 0? X sub 0 is the initial amount of pollution in Lake Erie. So how much pollution is in Lake Erie at the beginning?
5 times concentration.
Okay, so it's 5 times the concentration of what's in Lake Huron. But that's not quite right. We're missing something there. Consider if the concentration is like...
The concentration flowing out.
We'll get the concentration flowing out in a minute here. Consider that maybe the concentration in Lake Huron is like 8%. Then 5 times 8% wouldn't give us the amount of pollution in the lake, would it? I would have to multiply it by the volume of the lake to get the total amount of pollution in the lake. So I need to take 5C. 5C is the concentration rate, but it's not the amount of stuff in the lake. The amount of stuff in the lake is 5C times the volume of the lake. And the volume of the lake is 480. Five times 480 happens to be 2,400. So there's the amount of pollution in the lake at the beginning. So that one's weird because it's got this C in it here. In a minute we'll do another example where we have a definite number and we'll see how that works better. And then finally we want to know when will x of t, what do we want x of t to be? Well, ideally we would love to be at 0, but that's not going to happen. We want it to be twice the concentration of the other lake. So we want our total amount of material to be 2C times 480. Remember, there's still pollution coming in, unfortunately, from Lake Huron. It's just that the pollution is less. All right, so 2 times 480, 960. All right, so here's our differential equation, dx dt plus our rate out. What's our rate out? 350 divided by our volume. The volume is 480. X has to equal R. Our R is 350 C. All right, so there's our linear differential equation. We have x prime plus P of Tx equals Q of T. How do we solve? Find rho. Now, of course, I can reduce, right? 350 over 480 is 35 over 48. So rho is e to the integral 35 over 48t, or dt, I mean. So that's e to the 35 over 48t. Not much to integrate there. We just have a constant. So we multiply. We have e to the 35 over 48t x prime. I'll leave it as dx dt, I guess. Plus e to the 35 over 48 times 35 over 48x equals 350c times e to the 35 over 48t. Assuming I did everything correctly, the left-hand side should be the derivative, d dt, of our rho, e to the 35 over 48t times x. Equals 350c times e to the 35 over 48t. Is that right? Well, if I take the derivative, I leave this one alone, take the derivative of that one, that's the first piece. Plus, I leave the x alone, there's the x. I take the derivative of this one, the derivative of e to the power is e to the power times the derivative of the power. Looks right. Integrate. E to the 35 over 48t times x equals 350c. I integrate this, I'm going to have e to the 35 over 48t times something. Times what? What's that? Close. If I was taking the derivative, I would have to use the chain rule and I would multiply by 35 over 48, but I'm doing the antiderivative, so I have to divide by 35 over 48, or I can choose to flip and multiply. Plus, well, I don't want to use c because I already used c, so I'll call it k. Alright, so finally, well not finally, but we're getting close to the end here. I can divide through by this e to the 35 over 48t. X equals, let's see, 350 divided by 35 is 10. 10 times 48 is 480, so I have 480c. And then when I divide by this e thing, it reduces that e thing. Plus k over e to the 35 over 48t. What's left to do? Two more things we need to do.
You don't have an initial condition.
We do have an initial condition.
Oh, you do. So
X at 0 was 2400C. So we're going to plug in our initial condition, and that will allow us to figure out K. So let's do that. I'll go back up here because I'm running out of room. I plug in my initial condition, 2400C equals 480C plus K, because when I plug in 0 there, I get 1 on bottom. 2400 minus 480. K is 1920. So the solution to that differential equation is x equals 480c plus 1920 c divided by e to the 35 over 48t. Yes, 1920c. 2400c minus 480c is 1920c. All right, we're almost done. The very last thing to do is what we're trying to answer. We're trying to answer when will the concentration be reduced to twice that of Lake Huron. Currently it's 5 times Lake Huron. We want it to be reduced to twice that. So we need to plug 960C in for
X solve for C.
and solve for T. All right, so 960C equals 480C plus 1920c over e to the 35 over 48t. And things work out pretty well. 960 minus 480 is 480, I think. So we have, compare I guess, 480c equals 1920c divided by e to the 35 over 48t. How would you solve that equation? Multiply by the e thing, and then divide by that 480c. And notice when you divide by that 480c, that c reduces with that c. The c's finally go away. We don't have to worry about them anymore. E to the 35 over 48t equals 1920 divided by 480 is 4. Well, logarithm, right?
Yeah.
Not exponential. Logarithm. 35 over 48t equals ln of 4. So t is, I have the ln of 4. I multiply by 48. I divide by 35. It's going to take approximately 1.9 years for the concentration level to drop from 5 times that of Lake Huron down to 2 times that of Lake Huron. Yuck. Didn't like that one?
No, the father of the lake.
Problems would be my comment on that.
So we don't see any on that.
I didn't say you wouldn't see any on the test. I did not say that. All right, well, I don't think I have time to do another one today. So I will do another one tomorrow, and then we will start section 1.6 tomorrow. See you then.